In this video, we will continue our exploration of probability by considering what happens when a whole class tosses coins. If you remember from the previous video, you were asked to toss a coin 10 times and write down heads or tails in the order in which you got that. In previous years, we always got the whole class to do that, and we would count the outcomes and be able to display them. So we could calculate what would be the expected frequency for each outcome by counting the possibilities, how many different patterns there are, and how many different ways there are for each outcome to occur. And we could compare the theoretically expected frequencies by the empirically observed ones, how frequently, how much, how many times something actually happened. So if you recall the calculation for the probabilities for two coin tosses, there was one way out of 4 possible patterns to get 2 heads in 2 tosses, because you had to get 2 heads, you had to get heads in both tosses, and that's 1 out of 4, and that's 25%, which is the same as the probability for getting no heads and 2 tails. And there was 50% chance of getting 1 of each. The probabilities for 4 tosses were based on the fact that there are 16 different possible outcomes, one of which is all heads, 4 heads, and one is all tails. There were 4 different ones, so 25% for one's heads or one's tails. And we get this shape of expected probabilities for 4 coin tosses. And these are the actual numbers. This was observed in the class of 2018 and the class of 2019. So this is the proportion of people as a percentage, the proportion of students in class who got all tails, 0 heads. Looks like about 11%. And the proportion of people who got 3 times tails, 1's heads, and so on. In 2018, 2 of each, 3 times heads, 4 times heads. And in 2019, this is the proportion of people who got all tails, here all heads, 2 of each, and so on. So these are actual data taken from previous years. The expected frequencies, the probabilities for different outcomes when you toss a coin 6 times are plotted here. So you see that the probability for getting heads once or 5 times is about 10%. The probability of getting an equal number of heads and tails is just above 30%, and so on. These are the expected frequencies, and these are the actual observed frequencies as proportions for the 2 classes that we also showed before. So in 2018, this was the proportion of people getting all tails in their first 6 tosses. This is not a negligible number, so 6 out of 6, and then once heads out of 6, and then twice heads, and 3 of each, and so on for 2018, and then this for 2019. And as you can see, the actual observed data are not identical between the 2 years, but they're similar to each other and similar to the theoretically expected proportions. What about looking at all 10 coin tosses? These are the mathematically expected proportions that are calculated by counting the number of patterns in each case. And these are the actual observed data from the 2 classes. So if we join the observed proportions, we can see the shape more clearly. And we see that in both years, we got low proportions here, low here, and falling, and high proportions around the equal or nearly equal numbers of heads and tails. Similar but not identical between the 2 years and between the observed and the theoretically expected numbers. So, as main observations based on these actual data, we can say, first of all, the theoretically expected proportions are actually approximated every year. And this was true of previous years as well. It is why we do this experiment every year, because it always works. We approximate the theoretically expected proportion. Approximate means you're close, but are not exactly there. So if you think about this for a moment, it could be seen as a bit strange because there's a bunch of coins tossed by a bunch of people. Each coin toss is completely independent of each other coin toss. Comes up heads or tails regardless of anything. Yet in the end, if you take them all together, they resemble a mathematically defined shape. So it's like all the coin and all the times they were tossed conspire to produce something close to a very well defined pattern. It's as if they know about each other and communicate and say, oh, you got lots of heads, so I should get less heads. That's not how it works. Okay, obviously, coins don't talk to each other and they don't remember what they came up with in the previous time they were flipped. So this is not magic and this is not interaction. This is just probability. That's the whole point of going through these examples. The second thing to keep in mind is that different classes produce different proportions. So every year is different. There is variability in the actual outcome. The shape is not identical. So why would we not get the same shape? This is kind of the opposite question from the previous one. Think about, we have the same population, students in this class, and they do the same thing. They flip coins the same number of times. And there is a population target, which is the mathematical curve, how we expect these coin tosses to sort out probabilistically, and the outcome exhibits variation around that. So they approximate that, but they're not exactly that. And we can explore how that varies by asking the computer to play the role of different classes. And actually, this gives us a lot more flexibility in what parameters we can choose. But because coins are just random switches between heads and tails, and we can ask the computer to produce randomly zeros and ones, or essentially heads and tails, this is exactly the same as having lots and lots of classes. So we ask the computer to produce random events that are the same as coin flips from a probabilistic point of view. This makes it very easy to do it many, many times and watch what happens. And we can also observe variability. If many classes do this, how similar are they going to look? We can also observe the effects of different parameters. So small classes, large classes, a few coin tosses for each person, lots of coin tosses for each person. How does that affect the outcome? You can actually do this for yourself after watching this video by going to this link and trying out different combinations. So let's start with not very many people, so just 10 people. That's a small simulated class, and each person flips the coin 10 times. So this is one simulated experiment. And that is something that happened in my first actual simulation when I ran this through the computer and asked for this number of coin flips and then counted heads and tails in each sequence of 10, and then plotted them as this bar graph. And I got 2 of the 10 people having 3 heads and 3 people having 4 heads, and so on. Okay, then I ran this again. So it's like a different group of 10 people tossing, each tossing a coin 10 times. And that's what happened. And then I did it again a third time, and that's what happened. So you see that the outcome fluctuates a lot. It doesn't look very much like the previous or the one before that. What if we had more people flipping coins? So 100 students, simulated students, tossing a simulated coin 10 times each. This is my first simulated outcome. Let's have a different simulated group of 100 people. What will happen? This is what happened. Let's have a third group of 100 people. That's the outcome. So there's still fluctuation, but they're much more similar to one another. These groups of 100 people are much more similar to one another than the groups of 10 people. What if we had a really large class with 1,000 students, each tossing a coin 10 times? Well, this is one outcome, and this is another group of simulated 1,000 persons. These don't change very much. So if you have lots of students, if you have a very big group doing this, then the differences between the groups become very small. The result becomes stable and doesn't depend on the group anymore. If we had a class of 1,000 students and asked them to toss a coin 10 times each, the results between successive years would be very, very similar. Okay, what if they didn't toss the coin just 10 times? Let's just go back to our starting point of an actual class of about 100 persons, tossing a coin 10 times each, and simulate that once. Okay, this is 100 simulated persons tossing simulated coins 10 times each. What if they were to toss the coin 100 times each? And this is where it's actually not very convenient to try and do this in class because of how long it would take. The computer does it very quickly. So what happens is that each of the 100 simulated persons tosses a coin 100 times each, and you don't see anyone having heads 20 times, or 10 times, or 0 times, or 80 times, or 90 times. Let's go back to the 10 times to see what this means. So 100 people tossing a coin 10 times each. This is what we did in class, and we could expect to have a person every year getting 9 times heads or 9 times tails, which in itself is a bit surprising. We don't usually have someone have all heads or all tails in a class of 100. This would happen rarely because its probability is less than 1 in 1,000. But you see that you can have 9 times heads. So this means that you have 9 times more heads than tails if you flip the coin 10 times. The ratio is very large. You can have very different proportions. You can have 8 to 2, which is 4 times more heads than tails, or actually 9 to 1, 9 times more heads than tails, or 9 times more tails than heads. This is conceivable and indeed happens in a class of 100 to have a ratio of 1 to 9. But if they toss a coin 100 times each, a ratio of 9 to 1 would be like having 90 times heads and 10 times tails. This doesn't happen. A ratio of 4 to 1 would be like flipping 80 times heads and 20 times tails. That doesn't happen when you have 100 coins. Not even 70 to 30 is observed. So everyone gets a ratio that is closer to 50-50. It's not exactly 50-50, but it's closer to 50-50. What if everyone tossed a coin 1,000 times? Okay, now everyone is very close to 50-50. So if you toss very many times, then you can expect the ratio of heads to tails events to be close, very close to the mathematically expected 50-50, which is how likely the coin is to get tails or heads. Now, don't be misled by this histogram. This is a histogram now. And the bins are very wide. So from 450 to 500 and 500 to 550, there is a lot of different possible outcomes here, and there is actually a shape. Not all of these outcomes between 450 times heads and 550 times heads, these aren't equally likely, of course. And you can already think about this and realize that you'd be more likely to have 500 and 500 than 450 and 550. So a shape like that is hidden by the fact that the bins of this histogram are 50 wide. They're very wide. We'll see that shape later. But the point I want to make here is that when you toss many times, you expect the ratio of heads to tails to be close to the mathematically expected probability of the coin, which is 50-50. So there are two ways that you can get predictability from randomness in this simulated experiment. In general, the overall result of many random independent events is predictable. And actually, it's predictable with known confidence, and we'll get into that later in the course. For now, we can remember the two aspects of the coin toss experiment, which is if you have more and more people tossing coins, then you get closer and closer to the theoretically expected curve. What is the theoretically expected curve? It is the expected frequencies of occurrence of the events that you get by just counting how many patterns are possible and how many ways each outcome can happen. And the second thing is, as you get more events, so each person tosses more and more times, then each person's outcome approaches the theoretically expected proportion of 50-50. Why is that theoretically expected? Because the coin is fair, equally likely to land heads or tails. And I encourage you to go to this link and try the experiment multiple times with different settings to see the kind of variability you can expect and the kind of distribution you can expect.